Thank you. I'm Sam Scarpino from the Santa Fe Institute. So I want us to think for a second about where the next pandemic is going to emerge. And I'm going to use this as an analogy for how I like to approach the construction of these systems, especially with novel data. And I think thinking about the next pandemic is important because prior to 2009, at least for influenza, we would have been paying attention to this map, which is a map of H5N1 and bird populations, which are the reservoir for flu. And you'll notice that Mexico isn't even on this map. So the country it came from isn't even present on the map that we might have been using for surveillance. So if instead we just think a little bit more broadly about factors important for an influenza pandemic, we might think about things like air travel. So for a pandemic, it has to spread around the globe. Or we might think about biological factors like hogs, which are important evolutionary intermediaries. So if we look at this map of worldwide pig density, you'll notice that Mexico is in fact actually on this map now, so we're doing a little bit better. And in fact, if we zoom in on the map, you'll see that the central region of Mexico, in particular the Veracruz state, is lit up in red. The same is also true for the central part of the United States, which experiences H1N1 and H3N2 variant outbreaks every year, spilling over from pig populations into humans. And just a more recent example, it happened again with Ebola. I think if you'd polled the audience prior to the West Africa outbreak, they might have said Congo or Central Africa, or a list of some of the countries where Ebola virus has been seen in humans before. But going all the way back to 1982, these are data from Liberia, we have evidence for a fraction of individuals that are positive for Ebola-specific antibodies. And this has been regularly documented since the 1980s. So the idea that we're continually surprised seems a little bit surprising. And what we want to think about is that really disease surveillance stands at a crossroads as a result of all of these new data sets, but how can we leverage them and leverage our biological and medical understanding of these diseases to build better systems? And as I'm sure many of you are aware, we're advocating for a 4-step program, and I'll explain each of these a little bit more. Formalize the objectives, specify the data and acquire them, which is often a challenge, simulate data if you can where missing, and then select the most informative sources. So just as an example, one surveillance goal we've worked on is predicting influenza hospitalizations in Texas, which is the time series you're seeing. We have a very specific goal, which is to explain the variance in this time series using provider reports. Data sets that we might consider would be the influenza-like illness surveillance network seen on the left. These are primary care physicians in Texas. Each dot is a physician, the size, the number of cases. Google flu trends, or hospitalization data themselves. If we have missing data, we might try to simulate them, but one of the things when we're constructing these simulations that's important is to capture the most salient features of these surveillance systems. And in the case of ILI-net data, because they're voluntary, we need a reasonable model of provider reporting that captures this voluntary nature. And the final aspect, which is largely a computer science challenge, is to select the most informative providers. So if you want the 200 best providers in Texas out of 2,500 possible zip codes, you're not going to search over all of those exhaustively. You need a creative way to find them. And we gain novel insights. So for example, we found that Google Flu Trends is better in urban areas than rural areas. The pink dots are surveillance sites with Google, the green dots are surveillance sites without Google, and the surveillance sites with Google included are in much more rural areas. We also find that flu is harder to predict in more impoverished zip codes, and this relates to getting at the various factors that increase an individual's risk, not just age, but also things like the socioeconomic status. So darker blue means better prediction, lighter blue meant worse prediction. To sort of try to come up with a synthesis of these, we hosted a workshop at the Santa Fe Institute on enhancing disease surveillance with novel data streams, and we have a paper that we wrote that focuses on some of the challenges and opportunities. Many of the authors are in this audience. And we think this figure captures a lot of the important features, that we have these novel data streams that we want to use to predict disease incidence, inform public health action, but things like changes in disease severity, changes in press coverage, changes in behavior, all affect these data sources. We also identified a critical need for validation, so we identified 66 papers presenting new digital disease surveillance systems. Only one of them had open source code with validation. Only 26 did any sort of validation whatsoever. The last thing I'll mention, and you actually can't see this and it doesn't matter, but just as sort of a warning, We tried to build an early warning system from Twitter data using tweets about Lassa fever. And if you take 3 years of Lassa fever data, it's essentially flat with some blips, except in December 2014 where there's a huge spike. All of those tweets are about a music video that was shot in Lassa, Turkey. Not a single one of them was actually about Lassa fever in West Africa. So I think we have a real challenge just using sort of raw machine learning algorithms to build these surveillance systems. Thank you.